Welcome to this explainer. Okay, today we are tackling what is basically the ultimate mechanical dream of engineering. I'm talking about the historic quest to build heavy-duty industrial machines with absolutely zero friction and zero wear and tear. How? By using the invisible, almost magical power of magnetic levitation. I know, it sounds like pure science fiction, right? But this technology is actually operating right now, hidden inside the human body and out on our city streets. Let's get right into it. To really set the stage, just take a look at this quote. 0% friction, over 100,000 revolutions per minute. Just think about that for a second. In any normal motor with physical ball bearings or gears, that level of kinetic energy would generate so much heat it would literally melt the internal components into slag. But with magnetic levitation, or maglev, the moving parts never actually touch. They just float. It completely rewrites the rules of mechanical degradation and longevity. And the medical field shows us exactly why that zero friction rule is an absolute necessity. Consider the heavy brass and steel reality of a maglev pump designed for a total artificial heart. It operates on the same core principles as the famous HeartMate 3 blood pump. See, if you put a spinning motor inside a human chest, you absolutely cannot have physical bearings, because physical bearings will eventually fail. But by suspending this industrial-looking rotor completely with magnetic fields, it can continuously pump blood for well over a decade without a single mechanical failure. No friction, no wear. Here is our quick roadmap for breaking down the dense engineering that makes these levitating motors possible. We'll start with the zero friction promise, break down the operating principles and stator anatomy, objectively review the experimental performance results, and finally scale this tech from the microscopic all the way to massive urban infrastructure. Let's kick things off with Section 1, the zero friction promise and eliminating mechanical wear. So the crucial concept to grasp here is the self-bearing motor, or SBM. In traditional machinery, you always have two separate systems, right? A motor to provide the spin and physical bearings to hold that spinning shaft in place. Well, an SBM is this brilliantly ingenious design that just merges both of them. It's a unified mechanism where the heavy lifting of the rotation and the frictionless suspension of the bearing are exactly the same unit. Literally, the exact same magnetic fields making the machine spin are simultaneously holding it perfectly suspended in midair. Moving right along to Section 2, Maglev Motor Operating Principles, the blueprint behind the magic. To make sure this thing doesn't catastrophically fail inside, say, a human chest, the motor relies on three totally independently controlled axes. Step 1 is rotation control, which is what actually drives the pump. Step 2 is translation control. This constantly pushes and pulls the rotor axially to keep it perfectly centered. And step 3 is tilt control, basically an active countermeasure to stop the rotor disc from wobbling or pitching. By dynamically juggling these three axes, the system ensures the rotor never, ever touches the surrounding metal casing. It's really wild when you contrast the physical materials with the invisible forces doing all the work. You have this cold, heavy brass and steel stator sandwiching the rotor disc, but it's completely governed by a complex mathematical mapping of its X, Y, Z, and tilt axes. To maintain that tiny physical gap, digital PID controllers are sampling the rotor's exact position every 0.1 milliseconds. That means it is adjusting those invisible magnetic gears 10,000 times a second to hold that heavy center disc perfectly in place. Now, let's zoom in on Section 3. Anatomy of the stator, to see how this clockwork is engineered. This setup is incredibly precise. You've got 12 stator poles completely encasing the rotor. Then, there are dedicated 3-phase, 8-pole copper windings whose only job is rotation and axial movement. Completely separate from that, you have 2-phase, 6-pole windings, just for those tiny, precise tilting motions. And to top it off, they use Halbach permanent magnet arrays. That's a specific layout that massively boosts the magnetic flux density on one side. All this together provides the raw, brute force needed to manipulate all those independent axes at the exact same time without any magnetic interference. Theory and blueprints are awesome, but let's dive into our main focus today. Section 4, Experimental Performance Results. Let's see how these heavy components actually perform in the lab. When engineers physically pushed and disturbed this maglev design, the recovery metrics were honestly astounding. The axial translation settled time, meaning how fast the rotor restabilized perfectly in the center after a shove, was just 0.023 seconds. And the tilt control settled time was even faster at 0.019 seconds. To put that in perspective, that's practically instant. These incredibly fast settle times represent a massive victory over mechanical resonance. The system mathematically senses a physical wobble and corrects it before it even has a chance to cause a problem.
And during these double-stator axial SBM experiments, researchers achieved a clean maximum rotating speed of 3,200 revolutions per minute. They successfully pushed this heavy brass and steel design to immense kinetic energy levels without ever breaking the levitation field or running into control issues.
That physical stability holds up beautifully under pressure. Look at the data. Even when spinning up to thousands of RPMs, the maximum axial vibration amplitude measured a microscopic 0.14 millimeters. That's essentially the width of a human hair. The tilt vibration is just half a degree. That level of microstability is precisely why this heavy technology can be trusted to pump human blood without completely destroying delicate cells.
But the ceiling for this technology goes way, way higher. Variants of this exact Maglev design are currently used in high-vacuum turbomolecular pumps for semiconductor manufacturing. In a clean room, preventing contamination is everything. Because there are no physical bearings to shed dust or lubricant, these gaseous pumps have hit an absolutely staggering 28,000 RPM with minimal vibration. That's how they create the pristine vacuums needed for modern microchip fabrication. Finally, let's zoom out. Section 5, Scaling Micro to Macro. We are taking this from human hearts all the way to mass transits. Here we compare the microscopic with the massive. Think about the double-stator axial SBM used in medical devices. You have a complex stator physically enclosing a very small spinning rotor. But then consider the primary permanent magnet linear motor, which is engineered for mass urban transit. You go from a tiny circular pump to a miles-long train track. But the underlying physics of manipulating magnetic gears to achieve zero friction movement, absolutely identical. This linear motor adaptation basically flips the whole script. In this system, the expensive, dense permanent magnets and the armature windings, known as the short mover, they actually ride entirely on the train carriage itself. They project magnetic force downward against a really simple, rugged iron stator rail running along the track. By eliminating the need to wire miles of track with complex coils and instead putting the advanced hardware right on the moving train, engineers have built a super efficient system to levitate and propel heavy transit vehicles at a fraction of the cost. So I'll leave you with this final thought to ponder. As we successfully scale these frictionless magnetic gears from the super fragile confines of a human heart all the way to the massive demands of urban mass transit, what does a future world entirely devoid of mechanical wear and tear actually look like? If we can completely eliminate friction from our most critical infrastructure, what absolute limits of speed, efficiency, and longevity can our machines ultimately reach? Thank you for exploring this fascinating topic with me, and I hope this explainer gave you a much clearer view into the invisible forces powering the future.